All right, we now want to talk about vector components. And vector components are very important, and you will do this thousands of times in this course. So what do we mean when we say vector components? Well, a general description would be this. So any two or more vectors whose sum equals a certain vector, and we'll say V, are said to be components of vector V. So let me look here at two different areas. So we have what are called rectangular components, and we have non-rectangular components. Now, far and away, the most common one that you will work with are the rectangular components. However, the principle of components applies whether you're dealing with rectangular or non-rectangular. So let's actually start by discussing non-rectangular. We covered in our last video the fact that when we have two vectors, v1 and v2, and we add them together, we use the parallelogram rule of addition and then connect the starting point where the two tails separate to the ending point, or this diagonal of the parallelogram. Well, v1 has an associated direction 1, and v2 has an associated direction 2. And by the parallelogram rule of addition, it's clear that vector v is v1 plus v2. So v1 and v2 are really the components of this vector v along the directions 1 and 2. Now, these are not the most common types of directions to take. The reason they aren't is these directions are not independent. So I'm going to go ahead and write that. So these directions are not independent. Now, what do I mean by that? Well, what I mean by that is sum of the direction of 2 is also in the direction of 1. You know, if you look at direction 1 here, it is to the right. But if you look at direction 2, it is up and to the right. So it also has a rightward component to it that is captured really by direction 1. That is why in mechanics, and particularly in statics, the most common directions that you will consider are rectangular. Rectangular components are perpendicular to one another. This is what you are used to from physics, and these directions are really independent. And so you can see that very quickly as soon as you throw on an x, y coordinate frame. Let's use a highlighter there. All right, so we write this same vector v with respect to an x-axis and a y-axis. Now, there's some angle theta that gives us our orientation with respect to a reference line. We've discussed that. We said it was either a horizontal reference line usually or a vertical reference line. It's shown here off the horizontal. Well, the components of this vector v in the directions of x and y would be these two vectors, vx and vy. Notice that they obey the parallelogram rule of addition. So if you take vx and then you add vy to it and then connect the diagonal, or if you do vx and then vy, let's do it this way, you actually draw the vector, then when you put them tail to head, and connect the start point to the finishing point, you get the same vector v. So v is equal to vx plus vy. So vx and vy would be the components of the vector v in the directions of x and y. Now, if you were interested in this angle theta, then you should be able to see that using your trigonometry that the tangent of theta is equal opposite over adjacent. This side is Vy, so this is Vy by Vx. Additionally, the nice thing about rectangular components is when you draw this triangle, if you will, then you form a right triangle. And so the magnitude V squared is easily seen as Vx squared plus Vy squared. Now, if you think about the other trigonometric rules that you would have in here, you can look at the cosine of theta. The cosine of theta is equal to the adjacent side, I'll use Vx, divided by the hypotenuse, which in this case is V. And you can see that V times the cosine of theta is equal to Vx. The sine of theta for this triangle is the opposite, Vy, divided by the hypotenuse, V, so that V times the sine of theta is equal to Vy. Now, I want to urge you to look at this with caution, so we'll put be careful here, because a lot of times students see V cosine theta and V sine theta, and they always associate cosine theta with x, and they always associate sine theta with y. And that is not true, so you have to be careful. In this example, theta is adjacent for the x-axis, and it's opposite for the y-axis. So it's true that cosine would go with x and sine would go with y. But what if we had a different angle measured off the y-axis? Let's say some angle phi. So that is the Greek letter phi. And for this, if we were to look at our triangle here, well, now we have Vx on the top. And if we were to take phi, then the tangent of phi, let me write in green. So the tangent of phi would now be opposite Vx divided by adjacent Vy. We still have the same diagonal, so it's Vx squared plus Vy squared. But now if we were to look at the cosine of phi, well, that is adjacent Vy divided by hypotenuse V. So now Vy is V cosine phi. And if we were to do the sine of phi, that is the opposite, in this case Vx, by the hypotenuse V. And so Vx would be V sine phi. Now, here is the moral of the story. Whichever side, x or y, has the angle measured off of it, then the cosine of that angle multiplied by the vector is going to return that component. So for theta measured off of the x-axis, V times the cosine of theta is the x component. For phi measured off of the y-axis, V times the cosine of phi is the y component. That's always the case. Now, one other thing that I want to point out, it shouldn't be the case that x and y have to be horizontal and vertical. So x and y do not have to be horizontal and vertical. They are literally just reference lines that we choose. So for instance, you could have an x prime axis and a y prime axis. These are still rectangular. They're still perpendicular to one another. These directions are still independent. And so now, though, you have different components. You have Vx prime and Vy prime. These two components still add together by the parallelogram rule of addition to give this same vector V, but they are different components than Vx and Vy. For instance, you could choose a set of axes, we'll call it x double prime and y double prime, such that x double prime is in the direction of the vector V, and y double prime is perpendicular. In this case, v would be equal to vx entirely. The entire vector would be a component along this x double prime axis. So the axes aren't really that big a deal. But with rectangular, the important things are that they are perpendicular to one another and the directions are independent. We kind of skipped over the independence of the directions, so let's return to that really quickly. So for the x-axis here, the x is to the right, negative x would be to the left, the y-axis is positive up, and the negative y-axis is down. And so for this vector v, it points up and to the right. So that has a component that is vx positive to the right and vy positive up. But you'll notice that there's no part of vy that's in the direction of x, and there's no part of vx that's in the direction of y. That's not the way it was down here with v1 and v2. v1 was to the right, and v2 also had some rightward portion. vy has no left or right portion, and vx has no up or down portion. And so that's why we say that it is independent. Now, one last thing I want to show you here is how to write the unit vector that is associated with this vector v. We talked about that a minute ago. So here is some unit vector n, and so v has some magnitude times a direction n. Well, n is going to have to orient you in the x and the y directions. And the easiest way to do this is to take the vector v and divide by its magnitude. And so for us, this would be equal to v is a vx plus a vy divided by the magnitude. The magnitude is the square root of vx squared plus vy squared. But you'll most likely want to just write that as v. And so if we were to look at this, then this would be, well, vx, we wrote in a magnitude form here as v cosine theta. And if we divide that by v, we're left with cosine theta. And for vy by v, it's v sine theta by v. So that's just sine theta. So when we write this unit vector, v divided by the magnitude, that's equal to n. Well, then that's equal to cosine theta in the x plus sine theta in the y. Now, what does it mean to be in the x direction and in the y direction? Well, it turns out we have to give unit vectors for x and y. And you should remember this from physics. And the unit vector that tells you the x direction is I. And the unit vector which tells you the y direction, is j. And so when we write this vector, we can say, well, that's cosine theta in the I plus sine theta in the j. And so now, if you were to write v, well, this is v in the n. So this is v times the cosine of theta I plus the sine of theta j. And if you were to expand this, this is v cosine theta in the I plus v sine theta in the j. But v cosine theta, we said earlier, was vx. And v sine theta, we said earlier, was vy. But vx in the I is just vx, and vy in the j is just vy. And so the unit vector, n, is nothing more than a vector of magnitude 1, which points in the direction of v, and then you put the components of that vector in x and y. So 1 times the cosine of theta in the I plus 1 times the sine of theta in the j. It should be easy to see that if you were to take the magnitude of this vector, cosine squared theta plus sine squared theta, that would be 1. And so that's it. So that is the unit vector here for this vector v. Unit vectors are a little bit weird for most students up front, so don't worry if you're a little bit confused right now. I'm going to work with you on how to get unit vectors, especially in the next 2 videos. We'll talk some more about components, and I'll show you how to get some more unit vectors. So I realize this is a little abstract right now, so don't stress too much. Something that might help you a little bit is to recognize that you can write Vx and Vy in terms of magnitudes times unit vectors. So Vx is really some magnitude Vx in the I, and Vy is some magnitude Vy in the j, where I is the unit vector for x directions, and j is the unit vector for y directions. And so with that in play, this becomes, I think, a little bit easier to see. So that the other way we write Vx is V cosine theta in the I, and then Vy is V sine theta in the j. So that's maybe another way to help you see it a little bit. But we're going to do a lot of work with this, and really Chapter 2 gets into working with a lot of vectors. So don't worry about it too much. All right, I'm going to stop there for now, and then we'll discuss a few other things about components in the next video.